Okay, so let's see. First, we have to derive the ODE, right? We always have to do that. So let's draw out our control volume here. So we have our semi-infinite in this direction. This is the positive x direction. Over here, we have temperature as a function of time. So T initial plus beta T and H bar. So in here, let's do a control volume. Okay, so our control volume says we have Q dot X here, we have Q dot at X plus dx. And we have in here the partial U with respect to time. Okay, and then everything is initially at T initial. Okay, we can then do the energy balance, write that out. So that becomes Q dot X equals Q dot X plus dx plus the partial U with respect to time. Continue to expand this out, and we end up with 0 is equal to the partial of Q dot X with respect to X times dx plus the partial of U with respect to time. Okay, our rate equation for conduction is, this is for a plane wall. So we have Q dot at X is equal to minus K AC partial of temperature with respect to time with respect to position. And then our internal energy storage term is U, sorry, I'm getting sloppy here. Du d time is equal to rho C AC dx, right? AC dx is the volume. D temperature, D time. Okay. So that you've done several times now. So we can bring this all back together, and I'll just skip the step, but we end up with alpha, the thermal conductivity, the thermal diffusivity is equal to the following: d squared T dx squared is equal to d temperature, d time. Okay. And then in terms of boundary conditions, we have the initial condition. So the temperature at time equals 0 is equal to T initial. And then the second boundary condition, so this is 1, we need a boundary condition in space. Okay, so remember this thing is going off to infinity, right? It's infinitely long as far as the thermal wave knows. So if you go out far enough, you should find material that exists at T initial. Okay, so that's just saying that temperature as X goes to infinity has to equal T initial. Make sense? So that's our statement of the problem here. Okay, so then next thing is going to be, let's go through and, oh, sorry, there's one more, isn't there? So the third boundary condition, let's get all of these, careful here. So the third boundary condition is convection at the wall. And that's just H bar times the temperature difference, which is T initial plus beta T. That's the temperature at the wall, or of the surroundings, minus the temperature at the wall, which is T at X equals 0. That has to equal the conduction, which is minus K partial of T with respect to time, with respect to position X, evaluated at X equals 0. Okay, that's our statement. Everybody see how we got there? Okay, so here's our mathematical statement of the problem, and then the task is, transform this into the S domain. Okay, so we can go through and do that. Like it's a little different for 1D right now, because before we just had things where it's derivatives with respect to time. Now we have derivatives with respect to X as well. We have to worry about that. Okay. So let's see. Let's take first this up here. So let's take the Laplace of d squared T dx squared. And remember, T here is a function of X and time, right? So we're taking the Laplace of that derivative. So if we look at our table, I'm taking the partial of temperature with respect to position. So which of those is it going to be? probably going to be the last one, right? So we have the second derivative of temperature with respect to position. And so that just becomes the same thing again, but in the S domain. So this becomes d squared t hat dx squared. So we went from PDE to ODE in this position one. And this t hat's now a function of x and s. Okay, so continuing on, let's take the partial of the right-hand side. So that would be, we brought 1 over alpha. So that would be partial of temperature with respect to time. Again, this is x and t. So the Laplace of this is going to be 1 over alpha, that's a constant, times s times t hat, which is a function of x and s, minus t at time equals 0, which is t initial. Right? Okay, and then the last thing here is, let's see, what is this? Looks like the exact same. Yeah, okay. So I think we're set there. So we have the Laplace of the PDE, right? So moving on. Okay, so then the next step is we need to solve this expression here. Right? This thing, we need to solve this expression for T of S. So if we look at this, what do we have? We have an ODE, right? It's temperature as a function of position in S, but it's an ODE and it's a non-homogeneous ODE. Okay, well, we know how to solve that, right? We've solved those problems before. If you split it in the homogeneous part and the particular part, solve each of them separately in this domain S, and then add them back together. Okay, so I don't necessarily need to go through all of that given the amount of time we have left, but if you do that, you end up with, let's see. So the homogeneous solution for T hat, I'll just give you that. It's C1 times sinh of the square root of S over alpha times X plus C2 times cosh of the square root of S over alpha times X. Okay. One thing to watch out for though is, okay, we have sinh and cosh, but if you remember that those functions are actually equivalent to exponential functions. And in this problem, we have a semi-infinite domain. So we actually want the exponential version of this, because if you have an exponential of something that's going to infinity and it's minus that infinity, then eventually one of those terms is going to cancel out. Okay, so whenever you have a semi-infinite body problem, you always want to take the exponential version of this statement. So if we do that, it becomes C1 exponential of the square root of S over alpha times X plus C2 times exponential of minus the square root of S over alpha times X. Okay, so this is actually the one that we want here, this one. Okay, I'll just give you the particular solution. So the particular solution becomes T hat P. That becomes T initial divided by S. So you could convince yourself that that's the case, but I'll just leave it there. So then you add these things back together. So T hat is equal to T hat H plus T hat P. Okay. So now we have this general solution. We have C1 and C2 appearing. So now we need to enforce boundary conditions, right? But we have boundary conditions in the time domain, right? We left those behind when we were doing the conversion of the PDE into an ODE. We didn't ever deal with those, right? So now we need to actually apply the same transform to the boundary conditions and then bring those along with the analysis. Okay, so let's start here by, here's our statement again. So let's start by taking this one here, right? The first space one. So we have, let's see, if you do the transform, it becomes T hat as X goes to infinity is equal to T initial over S. Right? Okay, and then we have to substitute back that stuff back into our solution that we came up with up here, right? This solution. So we end up with T hat is equal to C1 exponential square root of s over alpha. We're evaluating this as x goes to infinity, so that becomes infinity here, plus c2 exponential of minus square root of s over alpha times, infinity. Okay, plus, what is this, t initial over s. Okay, so we're evaluating as x goes to infinity, so then we end up with the following, which is t hat is equal to, or this thing yields c1 times infinity plus c2 times 0, right? The second one goes to 0. That's equals 0. Okay, so in order for this to work out, c1 has to be 0. C1 has to be 0. Okay, then we're left with our solution t hat is equal to c2 exponential minus square root of s over alpha times x plus t initial over s. Okay, so now we have the second unknown coefficient. So we then need to do our second boundary condition here. Right? Again, I don't know, let's see, just with a couple of minutes left, I think you guys can probably do that. But the thing to point out is, as we're going through this, we have to transform this. Here, I'll give you this in s. So this becomes h bar t initial over s plus beta over s squared, right? Because that's beta t, right? So it becomes beta over s squared. If you look at your table, minus t at x equals 0, t hat at x equals 0. Well, that has to equal minus k dt hat dx at x equals 0. So that's the equivalent boundary condition in the S domain. Okay, so we go through and enforce that boundary condition. There's nothing really interesting about that, except that we end up with the final result here is t hat is equal to h bar beta over s squared times k square root of s over alpha plus h bar times exponential of minus square root of s over alpha times x plus t initial over s. Okay. Okay, so now everybody can wake up and look at this, right? Okay. So this is our solution. Is there a way that we can get this back into the time domain? Well, there's 1 over s squared, there's s in the square root, it's all multiplying some square root of argument in an exponential, so it's unlikely that we're going to find exactly this transform that gets us back. So this is where we go to use the Talbot inversion. So if you want to look at this probably on your own time, this is what we have, but we have this function. This is what we just did. I'm using the dot notation here. It should be exactly the same thing that we just did. And then I have this function that calls it. Okay, so I'm going to look at this for several different positions x over a whole range of time values, again, from a small up to 24 seconds. And we're gonna plot at different points the temperature. So let's do this real quick. Where did it go? It's hiding here, so let's do it again. Yep. Okay. So here we are. So you can see this is our solution now, what we just derived for this problem. This is temperature as a function of time for different positions. And you can see as the further deeper you and you get, the longer it takes to respond. Okay. So that's Talbot inversion. And it's a really useful tool. It's something you want to do on your homework. Okay. Thanks, everyone.